Okay, so we are going to do a little chapter 4 review. This is going to be a little explanation of certain problems on the review packet for Geometry 21. You guys all ready? Yay, all right, okay. So you're famous now, being recorded. Okay, so lesson 4.1 was just really the most important part of lesson 4.1 was to understand that when you write congruent statements, you have to pay attention to the corresponding parts, the corresponding order. So if this is S as the first letter and G as the first letter, that means that in the diagram, S corresponds with G. So the order matters, right? So angle S is congruent to angle G. So a congruent statement can be about angles, about sides. GR is the first two letters. So GR would be congruent to the first two letters here, SA, etc. Okay? If you are asked to write a congruent statement, like, I guess it doesn't ask you here. Well, let's look at this. Well, let's do number 7. Triangle REG. So they mixed up the order a little bit. Triangle REG. Well, if we look at this congruent statement up here, R corresponds with what letter? A, right? So since R is first here, A has to be first here. And then E corresponds with what letter here? T, so that would have to go next. And then G corresponds with S. So this would be REG, triangle REG congruent to triangle ATS. Everybody kind of get that? That is the big push for 4.1. That's the big idea. The other thing that was important in 4.1 was just the definition of congruent polygons. Remember, congruent polygons means that all the sides are congruent and all the corresponding angles are congruent. I should say corresponding. Corresponding, right? So that was the other thing that we really talked about. If you have two polygons that are congruent, then all the corresponding sides are congruent to all the corresponding sides on the other polygon. Okay, and then the angles as well. Okay, so in this section, I'm not going to worry too much about this section because this was kind of before we learned the triangle congruence postulates, right? So in this section from 4.1, they're really saying, are these two congruent based on that definition, that all the corresponding sides are congruent and all the corresponding angles are congruent. So when you look at this number 9, you have a right angle to a right angle, that's one angle. You have this to this, that's 2. You've got all 3 sides, so that's good. We're missing this angle to this angle. We did learn that third angles theorem. Do you remember that? Yeah. Third angles theorem in a triangle says that if 2 angles in a triangle are congruent, then the third angle of the 2 triangles has to be congruent. So this we would say, yes, these are congruent because we know all the sides are congruent to all the sides and all the angles are congruent to all the angles. We did have to use third angles to get that last angle, but we could do that. Okay. Here on number 11, they're saying quadrilateral XYZV and UTZV. Well, if we have this is congruent to this. They share this side, so that's congruent by reflexive. So we have all these sides are congruent to all the sides. You have a 60-degree angle there, 120-degree angle there. These two are congruent. Interesting, this one I think they want you to assume that it's a parallelogram, but we haven't really talked much about parallelograms yet. So like I wouldn't give one like that on the test because it's a polygon. We're mostly focused on triangles. It would be a yes, because if this is 120 and this is congruent, I'm trying to see. right? So these are congruent, and that's congruent. Then these have to be 120, and that has to be 60. So it would be a yes there. Yeah, yeah, mostly triangles on the test. Yeah. Okay, can you prove the two triangles congruent? So this was 4-2 and 4-3, where we really focused on SSS, SAS, ASA, and AAS. Those were the 4 theorems from section 4.2.4.3. So the important thing here is that even though in a triangle all the corresponding parts have to be congruent, we figured out that we actually don't need to know all of the parts. We can just know 3 parts, but they have to be a specific 3 parts, right? So what works? Remember we did the activity with the straws, the angles. We figured out, okay, side, side, side works. Angle, angle, angle doesn't work. Remember that? Right? Side, side, side worked. Everybody's triangles came out congruent. Angle, angle, angle didn't work because you could make a triangle like this, a bigger one like this. Even though these angles are the same, the triangles are clearly not the same size. You have a question? These types of questions will be on the test. Okay, so when you look at, say, number 13, angle to angle, that's 1A. Another angle to another angle, that's another A. And then you have a side to a side. That's an S. So 2 angles and a side. So then the question is it 2 angles and a side like this for ASA, or 2 angles and a side like this for AAS? Which one do you think this is? Yeah, Christian. ASA, because the side is actually touching both the angles. So in this diagram, so the S has to be touching both the A's in our postulate name or theorem name. Okay. Important here. I'm not sure it's shown as much on these. In problems like this, the 3 things that we really saw that we could mark without having to be told that they were congruent, right? So there's 3 things that were really you had to pay attention to. One was reflexive, right? So 3 things to look for or to mark in a diagram other than the given, right? 3 things that you can mark in a diagram that isn't like part of the actual given in your proof. In your proof, right? Reflexive property. If they share a side, you're going to look for reflexive. Vertical angles. If there's vertical angles, you can mark them congruent. Parallel lines. If it's parallel lines, we're going to look for certain types of angles. Commonly, it's alternate interior angles, like in this one. Sometimes you have corresponding angles, or I don't think we saw any alternate exterior angles, but like on the proof packet that you guys just did, there was one that kind of looked like this, right? And it said this is parallel to this, and this one is parallel to this one. So in these triangles, right, if this is the transversal, if you look at these 2 lines as being parallel, this angle is corresponding to that angle. So it gives you 2 angles that are congruent in the 2 triangles. Okay, and then it said that these were parallel as well. So then these 2 angles were also corresponding. So that gave us 2 A's, right? in our proof, I think the other thing that was given was that this was a midpoint. So then we knew those were congruent. So then we could use ASA with corresponding angles theorem. Yeah. We'll have to go back and I can try to find that proof. But it was given that the lines were parallel, right? So I can't remember the letters here, but if AC is parallel to DF, yeah, if AC is parallel to DF, then CF is the transversal, right? So if this was a statement of given, your next statement could be angle, oops, that can't be D, let's call it B. Angle BCA is congruent to angle CFD because of the corresponding angles theorem, which says if lines are parallel, then corresponding angles are congruent. Those would be the yellow angles there. That make sense? Okay. All right, so just remember to look for those three things and mark them so that when you get to problems like this, you know that's congruent. So then remember we said cover up one triangle at a time, which I can't do with you seeing it on the video, but if we cover up one triangle, this is going to be two sides and the angle between them, so SAS. You're going to want to check both sides though, I mean both triangles, so cover up one at a time. And make sure they match, right? This is SAS as well. Just make sure they match because sometimes they're tricky and they don't match the two sides. And then if one's different than the other one, you have to say no congruence. Yeah. Well, SSA is not a postulate, right? Because that's, but okay, so we mark this, right? I'm going to redraw it here. The question was, how do you know if it's ASA or SAS or AAS? How do you know where that S should go or where the A's should go? So in the diagram, these are two S's and an A, right? If the A is literally, the angle is literally touching both sides, right? Do you see how this one, the angle is wedged between those two sides? There's a word for that. It's called the included angle. It has to be the included angle, meaning the angle that's wedged between the two sides. That's SAS, because the angle, the A, is literally touching both S's. Well, okay, let's for this one, if we have two angles and the side is between them, the side has to be this side, right? For this one, if we have two angles and the side is not between the two A's, let me mark this the same. Starting with the same two angles, right? Well, now it has to be a side that's not between them. It can either be this one or the other one. But it's as long as it's two A's and then the S not between them. With SSS, that's obvious, right? With SAS, we just did the one with the two sides. The angle between them would have to be that one. If I did SSA, which we know is not a postulate, right? But in a diagram, what would it look like? It would look like two sides and an angle not between the two sides. Have to be either this one or this one over here. See that? So if you were given a question like this, number 13 through 16, where the diagram was marked, two triangles were marked like this, could they be proven congruent? No, because that's SSA and that's not a postulate, right? The only time that you might run across SSA that works is when what? It's a right angle. Ooh, everybody knows that one. And then what postulate is it? HL, right. Then you need a hypotenuse and a leg and a right triangle. Then you know it's HL, right? Okay, let's look at the next page. Oh, we have some proofs. That's good. Let's do some proofs. Has anybody gone ahead and done any of these and they want me to do a particular one, or should I just pick? Just pick a random one. Okay. Some of these are a little tricky, but you want to do 17 first? Okay. So px, oh, my x got cut off. The x is right there. Px is congruent to py. Zp bisects segment xy. So the first thing that you want to do when you approach a proof is mark the givens. You want to mark your diagram with the given information. Well, they've already marked px congruent to py. What does this mean? Zp bisects xy. What's going to be true because of that? Molly? Ym and xm are congruent. Very good. Now, look what triangles we're trying to prove congruent. We're trying to prove pxz congruent to pyz. Oh, this is a tricky one. It's a good one, but it's tricky. Okay, so xm and ym, are they a part of pxz and pyz? No. So what we have to do is use this information, the fact that xm is congruent to ym, to help us get what we need for the bigger triangles. So we're trying to prove these bigger triangles are congruent. Let me ask you this. In that bigger triangle, do we have any sides or angles of that bigger triangle? Samir? There's a side that they both share. So we kind of know that PZ is congruent to PZ, right? By reflexive. Do we have any other sides of those two big triangles? Part of our given. Yeah, PX and PY, right? So we know PX is congruent to PY. That's good. We've got two sides. Is that enough to say the triangles are congruent? No. So what are our choices here? If we have two sides, could we get another side and prove them congruent? Then we would have three sides. Does that work? Sure, you could get another side. That would work. Or could we get another angle? Could it be any angle? Which angle would it have to be? Which angles would it have to be? So in other words, here's our triangle. I'm drawing a little bit bigger. PXZ. We know this and this. What angle would it have to be? Have to be angle P. It would have to be this angle right here, because that would give me SAS. If it was this one or this one, it would be that bad word, right? So we can't have those two. So we have to think ahead here. And we have to say, well, if I know that XM is congruent to MY, are there two triangles we could prove congruent with that information? Maya? Yeah, we could get these two congruent, couldn't we? Right? Once we get those two congruent, could we say this angle is congruent to this angle? Oh, by what reason? Corresponding parts of congruent triangles are congruent. So if we prove the two red triangles congruent first, then we can say those two angles are congruent, and then by CP/CTC, then we can use those two angles to prove the bigger triangles congruent. Isn't that fun? That's like awesome. You guys are thrilled, I can tell. Okay, so see how just you got to plan out your proof a little bit first, and now we're going to write it. This is going to be challenging to write on this small spot. You guys might want to use a separate sheet of paper, because this is going to be a little bit longer, right? So we're going to start with our given. PX congruent to PY, and ZP bisects XY. Given. Now remember, we decided we want to prove these little two congruent first. So based on the fact that that's bisecting, we said we could say xm is congruent to ym. What would be the reason? Yeah, Risho. Good. Definition of bisector. What else could we say to get the two red triangles congruent? Because we only have two congruences now. We need another one. What else could we use? Yeah. Yeah. PM congruent to itself. Reflexive property, right? Now are we ready to say the red triangles are congruent to each other? Okay, so triangle PXM is congruent to triangle P, I'm watching my order now, right? PYM. What's the reason? Nope, because I'm proving two triangles congruent, right? Two triangles are congruent. What are my choices for when two triangles are congruent? Yeah. SSS. Remember, whenever you're proving two triangles congruent, it's got to be from this list of SSS, SAS, HL, all of those. Okay, so now we have the two red triangles are congruent. We did that for a reason. We wanted to use parts of those triangles. Which parts are we going to use now? Okay, so it's angle P, but it's two parts of angle P, right? So we can't really call it angle P. Okay, so angle MPX congruent to angle MPY. Reason? You know? That thing. Yep, CPCTC. Good. Corresponding parts of congruent triangles are congruent. All right. Well, let's switch to yellow. Ultimately, I'm trying to prove these two bigger triangles congruent. How close am I getting to that? Well, in this big triangle, I have PX to PY, that's one side. I have MPX to MPY, that's an angle. All right, so I got side, side, I got angle and angle. What else do I need? Okay, so what are we going to call that? Okay, so ZP congruent to ZP by reflexive. That gives me my third and last congruence. So now I can say my triangles are congruent. Triangle PXZ congruent to triangle PYZ. What's my reason for that one? SAS, side and angle between them. So SAS. That was a nice one, wasn't it? Two triangle congruences for the price of one. It's awesome. Okay. Let's do 21. You want to do a flow chart? That's a great idea. This video is going to be on the website, yes. Okay, so flow chart. On the test, you are asked to do, I think, 4 proofs, and it just says do one of them as a flowchart. So you can pick which one you want to do as a flowchart. It's got to be one of them, okay? So the best way to approach a flowchart proof is to start with your givens. So we've got LO congruent to MN as a statement that's given. Now you just kind of put a box around it and put given. They already marked this in the diagram for us, but we should always mark it ourselves. The second given is LO is parallel to MN. Again, that's a given. So we're going to mark our diagram with it being parallel. Okay, when they give us a given, they usually do it for a reason, right? I would say there would be a 1% chance, maybe a 0.5% chance that there's a piece of given that you don't need to use. So, how are we going to use the information that LO is parallel to MN? What should we be looking for? What should we be looking for? Yeah. Angles that are congruent, right? So we've got alternate interior angles, corresponding angles, same side interior angles, and alternate exterior angles. For the most part, with triangles, probably alternate interior and corresponding are going to be the most common. Okay, so if these are parallel, we're looking for some congruent angles. Before we look too hard for congruent angles, let's look for what triangles we're going to prove congruent. So we're trying to prove that angle MLN, that's this one, is congruent to angle ONL, that's this one. I'm not going to mark them as congruent. Remember, don't mark your diagram with the prove information. Only mark your diagram with the given information. I put little dots there just so I can focus on, okay, those are the angles I'm trying to prove. So probably we're going to prove 2 triangles congruent that contain those angles. So which 2 triangles do you think we're going to prove congruent? It's really only 2 anyway, but yeah, Molly. Yeah, we got this triangle congruent to this triangle. That's probably the best idea. So what we want to look for is what we know. We know that this side is congruent to that side, so we got one S already. That's good. We have to get 2 more pieces of information. The fact that the lines are parallel. What do you think is going to be congruent to what in this diagram, based on those lines being parallel? What do you think? Yeah, you. Okay, what would they be called? Like which ones? Name them specifically. If this is parallel to this, which alternate interior angles could we use? Angle M, N, L, that's this one. And that would be congruent to angle, just watch your order, right? If we start at M and go to N and end at L, we have to start at, yep, angle O, L, N. That's good. And that is because the lines are parallel. So directly from that given, that the lines are parallel, we are getting this conclusion that the 2 alternate interior angles are congruent. The reason? Alternate interior angles theorem. All right, well that's good. We got 2 pieces of congruence now, but that's not enough. We need 1 more. What else are we going to do in this diagram? What do you think? Look at the 2 triangles. We have this side congruent to this side. We have this angle congruent to this angle. What else What else could we get in these two triangles to be congruent? Remember the three things I said to look for. Reflexive, right? So this one has a side that they share. Well, that doesn't really come from one of the givens. So that's kind of going to be floating out here by itself. Ln is congruent to, we have to flip-flop it in this case, NL by the reflexive property. So now we have the three pieces of congruence information that we need in our diagram. 1, 2, 3. In that triangle, if we cover up one triangle at a time, what postulate or theorem can we use to say the triangles are congruent? What do you think? Yeah. Okay, so we're going to take this piece of information, and this piece of information, and this piece of information, and we're going to point them all to the fact that the triangles are congruent. Yeah, we're not done. So, in a flowchart proof, when you are proving two triangles congruent, you should always have three arrows pointing to that box that says the triangles are congruent. Even if it's HL, there's still three arrows. H congruent to H, L congruent to L. And what's that other third thing that we need for HL? Christian? Okay, right triangles, right? Not just enough to say there's right angles, but use the fact that there's right angles to say right triangles are being used for HL. Okay, but this case, we had three congruences, and we said, what did we say, SAS? All right, but we're not done because that's not what we were trying to prove. We were trying to prove that angle MLN is congruent to angle ONL. Are we ready to say that now? Angle MLN congruent to angle ONL. What's the reason? Yep, corresponding parts of congruent triangles are congruent. Okay, yep. AAS, how?
There's two cycle triangles, MLN and ONL are also.
Those are what we're trying to prove are congruent. And they're actually only congruent as alternate interior angles, right? The question was, couldn't we say these two are congruent by alternate interior angles? But those would be congruent if ML was parallel to ON, right? Because we have to look for the Z. And the Z that forms those two angles are these two lines. And we don't know those are parallel. They haven't told us those are parallel. So that's why we can't use alternate interior angles for those two angles. It's a good question. Do you understand? Alternate interior angles, we always look for that Z. The top and bottom of the Z should already be told to you are parallel. If you trace the other two angles, this one and this one, right? This angle and this angle. If you trace those, you're talking about the top of this Z and the bottom of this Z are LM and ON. Nobody said those were parallel. So we can't say that those angles are congruent if we don't know those lines are parallel. Okay? Does that make sense? All right, let me just look ahead a little bit because there's a lot more to this that we haven't done yet. 4.5 is going to use the isosceles triangle theorem. 4.5 isosceles triangle theorem, and don't forget equilateral triangles. Kind of were corollaries to that. The theorem itself says if in a triangle two sides are congruent, then the angles across from those sides are congruent. Remember, it has to be the angles across from the two sides. It has to be the base angles, not the vertex angle. Okay, the converse is just the opposite of that, right? If the angles are congruent, then the sides would be congruent. Okay? What do we say about equilateral triangles? What does that mean? If it's equilateral, then all what? All sides are congruent, and then that means that all the angles are congruent, and then that means that all the angles measure 60 degrees. So automatically, if you know something is an equilateral triangle, you can automatically put these as congruent and label them 60. I mean, that would be automatic. Okay? Same goes the other way. If you know all the angles are congruent, immediately you know they're all 60, and you know that all the sides have to be congruent. Right? So it doesn't matter what you're given, you know all that information about an equilateral triangle. So when you look at a section like this where they're saying find the value of each variable, if this is an equilateral triangle and this angle is 2x plus 10, what's my equation going to be? 2x plus 10 equals what? 60. And then you just solve that algebraically. In 26, we've got an isosceles triangle. If those two angles are congruent, then this is 25, this has to be 25. Well, then what's this third angle have to be? Yeah, 25 and 25 is 50, so that means 130 up here. But they're asking for x. X is half of 130, right? So x is 65. Well, because they're marked congruent to each other. Yeah. I don't like that this one has one arc too. That should have two, in my opinion. But I don't. Sometimes books are inconsistent like that. Okay, we've got a couple proofs here with isosceles triangle theorem and its converse. I believe one of the, maybe both of them were in your packet. I think I might have put those in your packet. So we could pick either one, but number 28 is given that angle 5 is congruent to angle 6 and px is congruent to py, we're trying to prove that PAB is isosceles. So if what's the step right before PAB is isosceles going to be? This is a good proof. If I want to say, oh, well, that means PAB is isosceles, what would be the step right before it? What would make it isosceles? What would be true if it was isosceles? PAB, what would be true? Molly?
Seconds PA and B.
Yeah.
Oh yeah, PA and BP are congruent.
Yeah. So the step right before saying that these are isosceles would have to be that the sides PA and PB are congruent. So if we kind of work from the bottom up on this proof, I don't have room to do it here. I'll look at my paper and do it. Okay, so if we're kind of doing this from the bottom up, my last step is going to be that triangle PAB is isosceles. I want the step right before it to say PA is congruent to PB. Right? Because if those are congruent, then it's isosceles. What would be the What do you suspect is going to be the reason for PA being congruent to PB? How could we get those two things congruent? Yeah. Yep. Good. Probably CPCTC. If we could get this triangle congruent to this triangle, then we could say PA is congruent to PB by CPCTC. Well, so far we have an angle in each and we have a side in each. So what do we need? We need either another angle or another side, right? Look at this triangle. Do you know anything about that triangle? Risho? Yes, to say what? Aha. We could get that angle 1 is congruent to angle 2 by the isosceles triangle theorem. Does that help us? What next? It's beautiful. Okay, if we could get 1 congruent to 2, that's going to relate 3 to 4. Because if 1 is congruent to 2, and 1 is a linear pair with 3, that makes them supplementary, and 2 is a linear pair with 4, that makes them supplementary, then 3 and 4 have to be congruent. If we could get 3 congruent to 4, then we could say ASA. Okay, so let's go to this beginning of this proof now. We went to the end, now let's go to the beginning. Angle 5 is congruent to angle 6. PX is congruent to PY. That's given. What we want to do now is say that angle 1 is congruent to angle 2 by the isosceles triangle theorem. Since angle 1 is congruent to 2, and angle 1 is supplementary to angle 3, and angle 2 is supplementary to angle 4, what's the reason for that, by the way? They're supplementary because why? Linear pair postulate, right? Then we can say that angle 3 is congruent to angle 4 by the congruent supplements theorem. Remember we said if we have two sups, we could say they're congruent as long as they're supplementary to the same angle, or in this case to congruent angles. All right, now we've got 5 congruent to 6, px congruent to py, and 3 congruent to 4. If we look at our diagram, 5 congruent to 6, px congruent to py, and 3 congruent to 4 is enough to say that triangle PAX is congruent to triangle PBX. By ASA. So then we're ready to say PA congruent to PB by CPCTC. And then the triangle is isosceles by, what would be the reason? We have this triangle, triangle PAB. We know that PA is congruent to PB, so we're going to say, oh, all right, well then that makes it isosceles. Why? Yeah, Chris? Definition of isosceles. Make sense? Yeah? Okay, there's lots more proofs on here, but they are, the answers are on the back. Let's look, name a pair of overlapping congruent triangles in each diagram. State whether the triangles are congruent by whatever reason. Remember, the trick to overlapping triangles is to separate them out. So that's overlapping with this one. Once you separate them out, you're going to mark what you know, and you're also going to look for the reflexive. What did they share before you separated them? So we know that AR is congruent to AR by reflexive. Oh, wait a minute. Wait, they're saying AR is congruent to RO. Wow, this is a crazy one, isn't it? These are congruent. So this is congruent to this. And then they're saying that this is congruent to this, too. Which would make that congruent to that. This one's crazy because I think you could use SAS, SSS, or HL. If we have overlapping triangles, it's not going to look like that. Well, I mean, I'm not going to give you one that's like that. It's going to be a little clearer as to, you know, what do you know and what you don't know. Yeah, a lot of these are... Well, this one's okay. I like this one and this one. Right? For this one, we would separate out G, T, R, and G, S, O. And T is congruent to O. They have those marked here. And then they have this side, GT, congruent to GR. Wait, sorry, GO. And then you have to think reflexive. What did they share before you separated them? Was it a side or an angle? These two triangles. Angle G is what they had in common before you separated them out, right? They shared angle G. So angle G is congruent to angle G by reflexive. So then what would we use here? ASA. Okay. All right, let's look at the next section. Part 2. Find the value of x. Okay, this is all having to do with equilateral and isosceles triangles. Just be careful that you're noticing exactly what sides would be congruent. If these two sides are congruent, remember those two sides come together at the vertex angle. You might want to put a little dot where they come together. If you put a little dot where they come together, that's kind of marking the angle that's not one of the congruent angles. So if you kind of follow where they come together and then go back and mark the other two angles congruent. And then on this triangle here, right, these two come together here, so it's these two angles that are congruent. Just be careful that way. All these answers are here, so we got to wrap it up here. Just remember that all the angles of an equilateral triangle add up to, are all 60 degrees. Oh, this last one, determine what other information you would need. Remember, this is not what you already know from the diagram, but what would you actually need to be told. So for SSS, I would need AD congruent to CD because I already know AB is to BC and I already know the reflexive. So I would need that third side. To use SAS, I would need the angle between the two sides. So I would need angle ABD congruent to angle CBD. Okay? I Something where you have to give the third side, the third statement based on whatever postulate we're trying to use. Okay, that was a really long video, 50 minutes. Nobody's going to watch that. Okay, ta-ta for now. Remember, all of the things, answers are